introduction about him. Actually, I have 7 pages. It'll take some time, but okay, briefly, he is a professor in Augustine Fresnel professor at Institute of Peace.
Fringes. You are aware of Fresnel fringes.
Okay. The problem is that all the name is written in French. It's kind of challenging for me. Also professor at Ecole Polytech, also Center of National Research Science, CNRS, distinguished scientist. So he was born in the 1947. Slightly younger than my mom. He studied this Ecole Normale Supérieure at Kasha and University Orge. Also, he got the master and the PhD in the same university, Orge University, and in 1983. And he taught various the locations in the world, actually, including Orge University. Also, remarkably, he also did some volunteer service in Cameroon. Also, he did these many places actually. And from 1992, he became the CNRS senior scientist, served as a head of the atom optics in Palace Group, okay, at the Institute Optic Ecole Polytech Palazzo. Right? And his research area is the kind of the developing actually, changing slightly, but the earlier stage, he studied coherent optics, also the non-classical properties of light as test of the foundations of quantum mechanics. Also laser cooling of atoms, atom optics, and recently ultra-cold atoms. Okay, I just finished first page. And he has about 200 publications, and this among them 20 papers has been cited more than 100 times. Okay, so maybe I can skip all the publications. And he also wrote the many books. Okay, so for example, recently a book. All right. Also, he has CD audio, okay, not video, okay.
In French.
Oh, that's right. That's a problem. He received a lot of the memberships, of fellowships. Oh my God, award. Basically, he receives every second year. Okay, he received the big award. Okay, so including recent award was that the UNESCO Niels Bohr gold medal. I don't know in detail, sorry, but looks like pretty big. Okay, also he, oh my God, distinguished lectureships, Harvard, New York, oh my God, here and there.
And now Taipei.
Okay, anyway, so it's really great to have the great the scientist. Also, I'm hoping that you guys all recognize his distinguished lecturer or speakers. Okay, please thanks for coming. Also, let's give a big welcome to you.
Thank you very much, and thank you for inviting me to stop here in Taipei. And thank you for this warm, not to say very hot, welcome that I feel each time I walk in the street. Okay? Now I understand the meaning of a hot welcome. So this will be about this Bell's inequality experiment. That is to say, it was part of my, it was the subject of my PhD thesis, and it was finished in '82. So it's unusual that 30 years after one still presents these kind of things, but my experience is that it interests very much general audience, and in particular young students engaged in physics, and so I certainly agreed to give a talk on that, although nowadays in my group we are doing totally different things, for instance quantum simulators with ultra-cold atoms and stuff like that. anyway, this is a favorite subject for a general audience, so let us present this subject. So, the first question will be, how did quantum information emerge? Nowadays there is a lot of advertisement about quantum information, and we may ask, but why is it that quantum information emerged only in the recent decade, okay, or the recent 2 decades? And actually, we will go back to the Einstein-Bohr debate, Bell's inequality test, and entanglement. This will be the main part of the subject, and we will see how people, starting from this, in particular from realizing that entanglement is really different from any other quantum weirdness, then invented quantum simulation. And of course, we have big names in that story. Of course, Bohr and Einstein, okay? And one thing you could have mentioned, which seems, because everybody knows that there was this big fight between Einstein and Bohr. I not only have the Bohr gold medal, but I also have received the Albert Einstein medal. And I'm particularly pleased of that. Because they are really 2 fantastic physicists, so I'm particularly pleased. We have Schrödinger, we have John Bell, and this one you know, it's Richard Feynman, and Richard Feynman is one of the founding father of the quantum computing, new quantum revolution. Okay, so let us start. Well, first, a few advertisements. This quantum optics book, I am one of the authors, and I highly recommend you buy it, because each time you buy it, I get a few dollars. And you have in it all the explanation. First, you can learn the basic equation, and then all the developments about the kind of things I'm going to present today. And now about the foundation of quantum mechanics, I have 2 books to cite. The paper of John Bell about the foundation of quantum mechanics. If you buy it, then there is royalties for Mrs. Bell. Unfortunately, John Bell passed away, but his widow still receives money. And I received no money, but so for free, you have the preface I wrote in that book, which explain my feeling about this second quantum revolution. And this book, unfortunately, it doesn't appear well. I have to do better. A book by Nicolas Gisin, who is one of the active players in quantum information. And it's an excellent book, I think, Quantum Chance and things like that. Again, if you buy this book, you have for free a preface by Alain Aspect in it, and I don't have any royalty. So, quantum information. If you Google quantum information, well, I Googled it, this was more than 1 year ago. You get tens of millions of results, okay? And among these results, you find that quantum information as a journal, it has a front page of New York Times, so it may be very important, okay, a subject which has there is an Institute for Quantum Information in Caltech, etc., and MIT, etc., etc. So you find that it is really interesting. And you may ask the question, how did it emerge? And actually, it emerged in 1935, when there was this paper by Einstein, Podolsky, and Rosen, who discovered the phenomenon of entanglement I will describe. Niels Bohr, and from this, as I will explain, Einstein concluded that quantum mechanics is not complex. So the answer to the question was no, quantum mechanics is not complete. But Bohr immediately opposed and replied, after a few months, replied to Einstein. And at the same time, Schrödinger also wrote a paper about entanglement. And by the way, it's Schrödinger who invented the word entanglement, okay, to describe this phenomenon. So he realized that it was important. So this was in 1935, and then nothing happened for the next 30 years, I will explain, until John Bell found the famous Bell's inequality. And after Einstein had the intuition, and Bell demonstrated that entanglement is different. Different from what? Different from what has been the founding feature of quantum mechanics, wave-particle duality. Entanglement is something else. I'm going to try to convince you.
You know why Bohr used a small b? Same journal.
Well, I'm sure you know, there were copy editors, and it's probably a prejudice of the copy editor of Physical Review. You know, in good old days, you remember, you are just as old as me, so in good old days there were copy editors in Physical Review, and they would decide where would be the capital letters and the minus, so I have no idea. It's probably not Bohr, is it? This probably is the editor of Physical Review. Anyway. And then, as I told you, so John Bell was 65, and after 2 decades, entanglement, Feynman came with a statement, not only entanglement is different, but because it's different, it's more, we can do more. We can do quantum computing. So let us start with the Einstein-Bohr debate. So I hope everybody knows that a real founder of quantum mechanics is Einstein, because everybody knows of Planck in 1900, okay? But what Planck did was to make the hypothesis that exchanges of energy between radiation and matter are quantized. 5 years later, Einstein went much further. He said not only the exchange of energy are quantized, but energy itself is quantized, which is a big conceptual step. And so the role of Einstein in the development of quantum mechanics should never be underestimated. It is really one of the greatest family fathers. But something strange happened. As quantum mechanics was being developed by the so-called Copenhagen school around Niels Bohr in Copenhagen, with all the big shots coming around the Niels Bohr, Einstein was more and more dissatisfied with the way quantum mechanics was being developed, okay? And he began to argue not about the formalism. He fully agreed on the mathematics of quantum mechanics. There is no discussion about that. But he disagreed on the way people around Bohr and Bohr himself would interpret the so-called Copenhagen interpretation. And after many discussions about the first quantum feature, which is wave-particle duality, where Einstein tried to find self-contradiction in the reasoning with Heisenberg dispersion relation and things like that, and Bohr could always come successfully to show that it was consistent. Then Einstein, in 1935, came to something new, which is discovered. I will show you this phenomenon of entanglement, and based on this phenomenon of entanglement and based on the equation of quantum mechanics for entanglement, he came to the conclusion that quantum mechanics is not complete, should be completed, and Bohr disagreed, but you have to realize that this objection was underestimated for a long time until Bell's theorem. Okay, so let us start. The question that Einstein was asking is the following. Is it possible to explain the probabilistic character of the quantum prediction by invoking a supplementary underlying level of description that we call supplementary parameter hidden variables? What does it mean? Think of the distribution of the velocities of the particles flying in this room. We describe it with a Maxwell-Boltzmann distribution. It's a statistical description. It's convenient. It's good for making calculation. But we have no doubt, at least in the classical context, that each particle has a given velocity, okay? So if we were smart enough, we could, in principle, describe any individual trajectory of each particle, etc. This would be the underlying level. This would be the supplementary parameter. So in other words, the question that Einstein was asking was the following. Since quantum mechanics is making only statistical prediction, isn't it just a statistical mechanics of an underlying level? And what is this underlying level? And with the Einstein-Podolsky-Rosen reasoning, Einstein thought he had demonstrated the necessity to introduce this underlying level. Let us see how it works. So I describe here not exactly the initial Einstein-Podolsky-Rosen situation, which is done with particles, electrons, and things like that, but I describe an equivalent scheme which has the advantage that it is a scheme that I will also describe for experiments and which has been used to test these ideas. So the idea is the following. You have a source which emits a pair of photons. One photon is going to the left, one photon going to the right, and I draw them in different colors to make it clear that they can be distinguished. Okay, one is red, the other is violet, or one is green and violet, that doesn't matter. Now, on each photon I'm going to make a measurement of polarization. I hope most of you know what is a measurement of polarization. You have a polarizer with two output channels. If the polarization is like that, it goes in the upper channel. If it is perpendicular, it goes in the lower channel. For my colleagues in particle physics who may not know what is it's strictly equivalent to a Stern-Gerlach for 1/2 particle, okay? It lives in a two-dimensional space, etc., etc. Okay, and you get either +1 or -1 depending on two orthogonal results. Now, what is important? For a polarizer, as well as for Stern-Gerlach, I can turn it. So I have a parameter, A, which is just the orientation. Another parameter, B, for the orientation. And I'm going to do measurement of polarization on photon U1 and photon U2. And I repeat, so I launch a pair, and I look, and I detect either here or there, and on the other side, either here or there. The parameters are A and B, and I make a measurement. And I repeat 1,000,000 times, okay? And I do statistics. So I can first do statistics on single probabilities. So what P plus A is a probability to find +1 when this polarizer is orientated along A, and etc. Etc. P minus, P plus, P minus. Now, much more interesting is joint probabilities which give access to correlation. For instance, P plus plus of AB means what is the probability to get +1 here and +1 here when the two polarizers are in orientation A and B? By repeating many times, I can find this probability. Okay. At this point, I just described an experiment which has nothing quantum, nothing, no EPR in it. Now comes EPR. Einstein, Polowski, and Rosen discovered found in the very mathematical formalism of quantum mechanics that such a state is allowed. What is such a state? Here I have put axes. When a photon travels here, it is polarized perpendicular to the direction of travel, so it can be polarized along X or along Y. So this just means that photon U1 is polarized along X. And this means that photon U2 is polarized along X. So XX is a pair of photons polarized like that. YY is a pair of photons polarized like that. What Einstein and his colleagues find in the formalism of quantum mechanics is that because of the linearity of quantum mechanics, of the equation, if this is possible and that is possible, the superposition is possible. And it may look innocent, but it's very surprising. Because don't be fooled. This and that is not at 45 degrees or circular or something like that. It's two different things. It's a superposition of two different things. A pair of photons like that is strictly different from a pair of photons like that. As different as a dead or alive cat. You know, the Schrödinger cat. A dead cat is different from a live cat. Here it's the same. This is different from that. But quantum mechanics allows you to consider the superposition of this and that. This is entanglement. And you are going to see why this is interesting. Now, when you have that, you can easily do the calculation of the various probabilities for the measurement that we consider here. If you don't find it easy, then buy my book. I explain carefully. So you can calculate the single probabilities, and what you find for a state like that, it's quite interesting. You have 50% chance to find +1 and 50% chance to find -1, whatever the orientation of the polarizer. So it really looks like absolutely unpolarized light. Same thing you calculate on the other side, you find totally unpolarized. But if you calculate the joint probability, now it becomes very interesting because now we have a correlation. For instance, you calculate P++ and you find 1/2 of the square of the cosine of the angle between the two polarizers. So when the angle is 0, the probability is maximum is 1/2. Okay. So P++ equal P minus minus equal 1/2. And of course, p plus minus equals p minus plus equals 0, and the sum makes 1. So you are happy with the fact that the sum of probability goes to 1. But I claim that we have a very strong correlation. Do I have a transparency to explain that or not? No. So why do I have a strong correlation? I have a strong correlation for the following reason. Because 1/2 is not so impressive. But remember that the single probability, p plus of A, is 1/2. So a photon arrives here, there is the probability to go here is 1/2. Now the joint probability is also 1/2, which means that the conditional probability to find this photon here, if I have found the first one here, the conditional probability is 100%. There is total correlation. So the image is the following. If this photon is found here, I'm sure to find the other one here. If this photon is found there, I'm sure to find the other there. Total correlation. And you can check p plus minus is 0. So there is never this. This is a total correlation. So it's interesting, you know, you toss a coin, here you find head or tails. You toss a coin, head or tails. You look here, looks totally random. You look here, looks totally random. But if I get head, I have head. If I get tail, I have tail. Strong correlation. So we need a way to quantify, not quantize, quantify, give a number, give a quantity for correlation. And for this, we use a totally classical concept. What is the correlation between two random variables? So here I have a random variable, tossing a coin. Here, or plus 1 or minus 1, I have another. What is the definition of a correlation between two random variables? Is the average of the product minus the product of the average. I hope you know that. If you don't know that, ask your professor in statistics. Okay? And when you do it, you get to this formula. So this is totally classical. And now, in this classical definition of a correlation, I introduce the prediction of quantum mechanics, and then I find the coefficient of correlation which takes this form. Cosine of 2 times the angle. So if the angle is 0, the correlation coefficient is 1, which means total correlation. If the angle is pi over 2, I find minus 1. Minus 1 is also a total correlation, and the sign minus means that if I get plus 1 here, I get minus 1 on the other side. But because I have crossed the polarizer, I understand why I have minus 1 when I have plus 1. So I have this quantity, which is an interesting quantity, because after all, at the end of the day, we can measure. Okay. So the question is, quantum mechanics predicts a strong correlation between what happens here and what happens there for such a state. And my question, I am a naive physicist, okay? I'm not a smart theorist, okay? I'm not doing string theories, okay? I'm a very naive guy, okay? And I say, well, when I have correlations, I want to understand where this correlation comes from, okay? So I would like to know better. So for that, my question actually is this one. For me, understanding is having an image, you know, having something that propagates in space. I should start from the source, it goes here, it excites a detector. This is what I like to have. And the point is that if I start from the most efficient way of doing the quantum mechanical calculation, which, again, if you don't understand this formula, buy my book or another good book in quantum mechanics, and what you do, that you take the state vector describing the two entangled photons, you project on the state vector representing the outcome of the measurement, P plus plus, you square, and you get it. Okay. So far, so good. You get the right result, but you cannot make an image. Why can't you make an image? Because this happens in an abstract mathematical space. And I cannot make an image in our ordinary space from that space. So for me, it's not an explanation. For me, an explanation is something which happens in our space, not in an abstract mathematical configuration space. And so the fact that it cannot be done is annoying, and many theorists, including, for instance, Asher-Perez, who was a famous theoretician in quantum optics, was a strong follower of Bohr and the Copenhagen school, but he made this strong sentence: quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. Okay? And I insist on having an image in the laboratory. And for that, I can develop another way of doing the calculation. it's a little more complicated. So if the professor comes with an exam where he asks you to calculate take the first method, okay? It's fast, you don't understand anything, but it's fast, you get the right result. If you want to understand, take the second approach, which is a little more involved. It's still totally correct quantum mechanics, absolutely standard, okay? But we will understand better. So we say, let's suppose that this polarizer is a little closer to the source than the other one, so measurement will be done first here. What can happen? I can get either +1 or -1. Initially, the state vector was that one. But then what should I do? When the measurement happened, the famous collapse of the wave vector. But the collapse of wave vector is written in any good book of quantum mechanics. So I open my book and say, what do they say? What they say is just after the measurement, I have a projection of the initial state vector onto the eigenspace associated to the result. The point is that if I get result +1, the projector is as a certain form, and if I take result -1, the projector has a different form, which means that depending on the results that I have found, after the measure, I get either this or that. What does it mean? Here, I made a measurement along A. If I get plus, it means I find polarization along A. And then the initial state vector in which the second photon was unpolarized just after the measurement, now my second photon is polarized in the same direction that the one I found for the first. But if I find -A, which is orthogonal to A, just after the measurement, the second photon is polarized perpendicular to A. This is what it tells you. And then it's very easy because the rest of the calculation is just applying the malus law for the second polarizer, and I get exactly, I don't go to detail, I get exactly the same results as the result obtained directly with a simple calculation. But now I have an image in real space because I see what happened. Until the moment when the measurement is done, I don't know, but just after the measurement, then the second photon knows what it has to do. So we have an image in real space, but of course there is a slight problem with that image. And Einstein was unhappy with that image because Einstein had in mind the fact that quantum mechanics implied such an image. And so, of course, the problem was that the measurement on the first photon seems to influence instantaneously at a distance the state of the other photon. And this seems to contradict relativistic causality, and this is why Einstein could not accept that image. Okay? So what can you do? Well, in fact, when you have strong correlation between distant measurement, there is another way of explaining it. And I'm going to show what is this way. It's a classical image. And to make you understand this classical image is, look, when the two photons are produced in the source, they have something in common. And it is that something that propagates and that determines the result of the measurement. We are going to make a small experiment. Everybody watches, please. The one who sleeps, wake up. At 3, you wake up and you watch the screen. 1, 2, 3. What did you see? You didn't see anything? Is green blind? Somebody who can see green. What did you see? Green spot. What did you see? Green spot. Wonderful. Strong correlation between what he saw and what he saw. Isn't that magic? No, it's not magic because I have a full theory for that. I can explain you, it's explained in my book, how the laser works. Then I can explain you how, because of Maxwell equation, light propagates, go to the screen, is scattered from the screen, goes to your eye, go to your eye. Of course, I'm not a neurobiologist, I cannot explain how it goes to your brain, but we assume it works, okay? And I have a full description. That was the idea of Einstein. Einstein said, to understand this crazy correlation, there is a simple way, is to assume that from the beginning, the two photons has a common property. But now there is a catch. Because some photons are polarized like that from the beginning, it will give these results. Other pairs of photons are polarized like that from the beginning, it will go down. So I have two different species of photons. But in the quantum formalism, They are all described by the same state vector, which means that by doing that, I am introducing supplementary parameter. I am completing quantum mechanics. So this was the reasoning of Einstein. If you want to understand in a reasonable way, not introducing crazy, faster than light stuff, then what you have to do is to complete quantum mechanics to introduce supplementary parameters. This was